Good morning, ladies and gentlemen. Welcome to the course of quantum transport. The course already in its final stage. Still, there are interesting topics, new topics to talk about. Today, we will talk about tunneling, electron tunneling, so that quantum transport in electromagnetic environment. This is a topic which is first related to interaction. It will be based on the concept of Coulomb blockade that we have studied once. You remember. And by another end, it will be related to dissipation in electric circuits which encompass nanostructures. And we will reveal very interesting picture of tunneling in the presence of this electromagnetic environment, which provides dissipation, accounts for energy loss of transporting particles. We will talk first about electron tunneling in normal metals, and that's the knowledge which we acquire during that will allow us to consider more interesting and exotic situations. We will understand the influence of environment on charge qubits. We will look at Jefferson physics. We will look how Cooper pairs would tunnel in the presence of electromagnetic environment. And we also look at tunneling of the superconducting phase itself. So all these cases of tunneling are in electromagnetic environment, external circuit, and can be treated, understood in rather same way. All right, good. So let me formulate a simple problem. Consider a simple circuit, which is here. So what do we have here? We have here tunnel junction, and we will consider electrons which hover this junction. Why do they hop? They hop to this node. It's perhaps an island. And indeed, if I would break the circuit here, it would be a Coulomb island. Then you remember what happens. It requires finite energy to put an electron to this island, and energy which is required to charge the island. So there will be no current at low voltages. It will be blockaded. Another limit, if this conductance is not broken but eventually large, so it can be just replaced by a wire. All right, what do we have in this case? In this case, the capacitor is not relevant whatsoever. And we just tunnel between two leads. So we expect elastic tunneling and Ohm's law. Good. Those are cases which are I draw in a bit more careful way on the right. So this is the case of elastic tunneling. Large conductances here, small resistances. And we expect electron just from the field states, which are shown on the right, go to empty states if there is a voltage difference applied to the junction at the same energy. If there is a Coulomb blockade, you remember one has to pay energy to charge the electron so that incoming electron would have to give some energy to the capacitor to charge the capacitor. So it will go at lower energy. And if voltage applied is smaller than this energy cost, there will be no transport. All right, there are two limits, and what I would like to understand what is in between at some moderate value of this conductance. There must be some smooth or perhaps sharp transition between these two states. I would give you a second to think how this transition could occur before kind of telling how does it actually occur. All right, a second. Well, for me, the most, if anybody would ask me such a question, perhaps my first reaction would be, well, this energy diminishes and becomes zero in this limit. That's plausible answer, but the real answer is more complex. The real answer is P of E. What does it mean? In both limiting cases, we consider very certain energy losses, which was zero for elastic tunneling, which was equal to Coulomb blockade to charging energy for Coulomb blockade gas. In between, we don't have a definite energy to lose. Rather, the situation is characterized by probability to lose certain energies. That's what I put here in the plot. So there is an incoming electron at certain energy, and it tunnels, and after tunneling, it can go at different energies. So the actual energy would be distribution would be different for every tunneling event. Good. We will understand how this function looks like. But let me note that even before I understood this, I would be able to compute tunneling rates. How would I do this? It's not complex. Look, what is the current I have incoming electrons on all the energies, and I have empty spaces here. All right, blocking factors. There must be empty space for electron to tunnel. Good. And normally I would put these two energies at the same level, But if there's a probability to have energy loss, I need to connect it like this. Okay, that's the formula. So, non-trivial element which defines a phenomenon which is called dynamical Coulomb blockade, that the energy which one has to pay for tunneling is not zero and is not constant. Rather, it's a stochastic variable, and situation is characterized by distribution probability to have an energy loss. Right, let us change a bit our setup to get a better notion of this probability, to get better understanding. So instead of conductor, I would put here an inductor. So an electron actually tunnels in the presence of an oscillator. Then it is clear what can it do upon tunneling. It can excite the oscillator, either excite one quantum, two quanta, three quanta, and so on, with some probabilities. So the whole function P of E consists of delta functional peaks equally separated with some probabilities. All right, I don't want to derive it now. I don't want to talk much about this. It's is sure that these probabilities are derived from Poisson distribution. As you remember, Poisson distribution is something which characterizes independent processes. So one could imagine that these quanta are lost independently, are given independently to this oscillator. So here we have a formula for probability distribution. I guess it has to be K here, right? It has a parameter. It has a parameter which I would like to concentrate upon. This parameter is a ratio of charging energy to oscillation frequency. Right? If we would really have to pay charging energy per each tunneling, that will give us average number of quanta which we excite. Changing the properties of the circuit, changing capacitors and inductors, one can have different values of this parameter rho. Let's look how this modifies the distribution. All right. Let us assume that this parameter is small. Then mainly electrons can tunnel without exciting the oscillator. Well, there's some probability to get one quantum, very small probability to get two. This is for this value of the parameter. Well, if you increase the parameter, you have more probability um, uh, to excite a bigger number of contracts and less probability to not excite anything. So the average of this distribution, as you can see visually, is somewhere around 1. Fine, let's increase this n bar even further. What will happen? Well, we will have a rather centered distribution, centered at something around 4, as we expected. If we go on and on, if we increase n further, then there will be again Poissonian distribution, and we have seen no, it was in another case. In the limit of large n, we will have a peak of the distribution at something around n bar. The spread of the distribution can be estimated. Oh, who can guess? Perhaps you remember something about Poisson distribution from another course or from yet another course. Or you could just get good guess from your first year practical. Year 1 over square root n. And this is very good. Yes, that's comes from the fact that Poisson distribution comes from independent parameters. The only point that 1 over n is relative accuracy. As to the spread, it is square root of n. So to get relative accuracy, we divide square root of n by the value itself, and we get what Sasha wrote. Good, so at big value parameter, Poisson distribution becomes Gaussian distribution, which is centered at an average, and which has spread of the order of square root and average. Fine. Right. I promised by the title of the slide to explain why and how it is a Poisson distribution. More scientific answer relies on the concept of coherent states and sudden change of oscillator positions. Recently, I talked about this in the course of advanced quantum mechanics. Here we don't go that far. It's more important for us to understand the qualitative answer, which is almost elastic tunneling at small n and almost certain at small n bar and almost certain energy at big n bar. Fine. That was for a single oscillator. Let me apply this to the circuit in question. Let me compute transport through the circuit at different voltages corresponding to these distributions. Right. If voltage is low, I have only elastic tunneling. And the probability to tunnel elastically is smaller than 1. So, yeah, smaller than 1. it is suppressed. So conductance, current and conductance is eventually suppressed here. When I increase voltage up to certain energy, I can already emit one quantum. So I have more probability to tunnel. So for this particular case, for oscillator model, we have differential conductances, which increase step by step when we get an opportunity to meet n quanta to the oscillator. Fine. These different curves, A, B, C, correspond to different values of this parameter and bar. Let me remind what it is. Right. Again, this is 0. A corresponds to 0.25, B1, and C4. So you see that the conductance is not, didn't change much for small values of n bar, and is almost completely suppressed for bigger n bar. Good. This is the conductance. Now integrated, I got current. And although these curves are made of the lines, they're obtained by integrating of this step-like function. Visually, the curves are almost smooth. So ideally, we expect to have Ohm's law, this diagonal. But in fact, we have a curve which always go a little bit below the diagonal. And if a bar is sufficiently big, the suppression of conductance is more than visible. All right, topic comes. In a particular model, when we employ only an oscillator. Now, I would like to give a notion which perhaps is somehow unexpected, but perhaps you know that any circuit, including dissipative one, can be presented as a big collection of the oscillators. So let me outline how does it go. Again, it's a crash course. Just explain what is going on without writing crazy formulas. This is an oscillator. We excite it with the current. We get impedance of the oscillator. So voltage source gives us voltage, current source will give us a voltage response. Resistor, that resistance will depend on the frequency. And for single oscillator, we just have delta functional peak to at the oscillator frequency. Dissipation will occur only this frequency. Let us modify the oscillator a bit. Let us add a small resistor to here. What would it change as far as the impedance is concerned? Well, this delta functional peak will become a Lorentzian, will acquire some finite width. Now let us postulate that only the total impedance matters for our situation. It doesn't matter how do we make this impedance, how many inductances or capacitance or resistors we would put there. Only impedance would matter. Then we can actually make any impedance by combining many oscillators, making continuous spectrum of these oscillators, making the distance between the frequencies of these oscillators smaller than the base of these peaks. All right, sir. That gives us the notion that any circuit can be seen as a collection of oscillators, and an oscillator is simple. Its quantum mechanical description is very well known. So we can quantize in this way any dissipative circuit. Fine. And we employ the same quantity P of E to understand electron tunneling in an arbitrary circuit. Okay. This is the expression we have. This expression is perhaps a bit complex, but one can analyze it and draw conclusions. Okay, it's a function of energy, and it is obtained as a Fourier transform of a time-dependent function. Okay, this is exponent of Fourier transform. This is this time-dependent function, and this time-dependent function is an exponent of the following time-dependent function, J of t. And J of t can be presented in two ways. First representation. For each mode from infinity, we have average number of quanta which we can emit to this mode. And we take it with a weight corresponding, with an exponent corresponding to the frequency of this mode. The same expression can be presented in terms of the impedance of these oscillators. It can be written like this. So what comes is an impedance of the circuit. Okay, but we want to have here dimensions expression, and to make it dimensionless, our old friend, okay, old meaning we have met him, of course, at this course only. Our recent acquaintance, conductance quantum, comes to play. Sir, you remember that I switch the topics of the course many times, but any time we have conductance quantum coming into play. Conductance quantum is a measure for an impedance of the circuit. If GQ Z is small, impedance can be disregarded. If it's large, then it does something. Right, so how about this function? There are two typical behaviors of this function as a function of energy. If you just don't look like at zero energy, they look pretty much the same. There's some distribution which vanishes at high energies. Yeah, of course, it has to vanish because its probability, if you integrate it over energy, it should give you one. The real difference comes at zero. In the distributions of one type, we have delta functional peak at zero. We have large probability of elastic tunneling. But there are situations when this is not possible and we don't have elastic tunneling whatsoever, like in Coulomb blockade. Right. Borderline between these two peaks is eventually the case under consideration, ohmic case, where the type of the curve would actually depend on resistance of the circuit. Good. So we have quantized electric circuits and we understood how energy losses in general upon tunneling can be expressed in a general circuit. It all depends on the impedance, frequency dependent impedance of the circuit. Fine. So let me elaborate on this practical case and the case of ohmic dissipation. Important parameter here is that the resistance which we have, perhaps it was to redraw the circuit. So we have tunnel junction to tunnel through. We have a capacitor. But what matters is this resistor. All right, and it all depends on this resistor and the behavior of probability of lost is a power law function with a power law exponent depending on the value of this resistor. Good. Okay, there are several examples. I want to zoom in. You have to be rather careful sometimes. The zoom breaks down when I do this, so be ready for an interruption, but I think I have to zoom on. All right, that worked. Nothing has disappeared. So what you see here are curves of P of E, and low energies, they have different power exponents. Curve A, well, it has a negative exponent. It kind of increases at low energies. Curve B has zero exponent. And for the curves, yeah, it's difficult to see the exponents. So I'd rather, oh, that's the wrong slide, sorry. I'd rather redraw the same plot in a double log scale. And in double log scale, any power law is a line. So you can see that all these cases, correspond to different power laws. So what I vary from curve to curve is this parameter alpha. Fine. Kind of memorize this picture. We will see it at least one time further in the course. Good. Let us take this P of E and let us put it into the formulas which will give us electric current. Fine. It turns out that at zero temperature, I don't have formally, I don't have Ohm's law. For any situation, there is an addition to this Ohm's law. Different exponent. Right, if I look at differential conductors, I would see that in any case, voltage differential conductance at zero is zero. But for different values of alpha of this resistor, it changes differently. So right curve, small impedance, it doesn't touch, doesn't differ much from one. And the conductance is strongly suppressed here, almost zero till certain value for big values of the impedance. Good. In the same way as for oscillator, we integrated over voltage to get IV curves. And eventually we see that the curves look, in fact, rather similar to what we have obtained from a simpler model of oscillator. So there is Ohm's law at low impedance. At high impedance, we don't have any current till charging energy, and then it rises up. And curves at intermediate impedance just lie somewhere in between. Fine. Fine. So we understood how electrons tunnel in the presence of electromagnetic environment. Good intuitive picture to have in mind that when electron tunnels, it is coupled to these environmental modes, and it needs to excite them. And thereby, therefore, this requires energy. And if it doesn't have this energy, it cannot channel. But this is probabilistic process. The energy which is required from this electron is different from case to case. Is given by this P of E, so that there can be, for instance, suppressed current at any voltage. Good. I hope we understood this. If there are any questions, please put them to the chat. We still have some time before the break. So let me start with a little bit different system. I don't want to look at the transport. Rather, I want to make a simple qubit charge qubit. So here I have two islands, and I would make sure by, for instance, implied gate electrodes not shown, that the energy of an electron in this islands, the energies are aligned. So the system can be with an electron either in left well or in the right well. Two states. And there is tunneling between these two states. So there can be a qubit. An electron can be delocalized between these two wells because of tunneling. Fine. In any case, I would like to work with isolated system, which has two discrete levels. And look, I put it to electromagnetic environment. It consists of different capacitances characterizing these islands. What's important for me is this resistor. Having the circuit, I would like to understand what is an impedance which is felt by tunneling electron. This is a bit tricky, but can be completely understood from a theory of electric circuits. So in this case, we just apply contacts to these 2 points and measure effective high frequency impedance. What I say here is to explain this. In fact, the impedance which is felt by this tunneling electron is not literally this resistor. One has to look at the capacitor network, understand how voltage is divided between different capacitors in the circuit. But after that, we just have some effective Z, some effective resistor. All right, that's a model, and we will be able to implement the function which we already know, function P of E, to this two-level system. Right. That will give us the rate of decay from upper state to the lower state. It's logical if these energy levels are separated by energy epsilon. Yeah, it's logical because one has to, in order to have such a transition, one has to give this energy to the environment. So this is proportional to probability to give this energy to the environment. Fine. Another quantity to look at is the probability to find the probability of de-localization. Remember, if we talk about normal qubit and levels are aligned, it's completely delocalized. It is neither in the left or right well, it's in a superposition of two states. And this will be a measure of delocalization of this qubit. It's also expressed in terms of P of E, but yeah, there's some integration involved. Good. So we made the system. We know already P of E, and we would like to understand what electromagnetic environment does to our system. I guess it's good time to have a break for, say, 7 minutes till 9:40. So, ladies and gentlemen, let's go on. Or I have to get it. Have to share screen. I need 2 steps for this. Right. Right, now the question of Sasha. Oh, I guess it was something I should have noticed earlier. Could you repeat why, as we start, why we divide by epsilon squared plus epsilon squared for the probability instead of just taking P of E I. Okay, you mean this formula? This is probability of delocalization. This is probability to find a qubit in wrong position. It is not an actual tunneling process which comes here. Rather, those are virtual processes. Virtual processes whereby, it tunnels here and it goes back, but there's some probability to catch electron here in the higher energy state. This is the localization probability. It is proportional to tunneling amplitude. Good. So here we are talking about virtual states. And the probability to get to this virtual states is also controlled by probability to have different energy loss. But the energies of these virtual states can be different, and we would need to integrate over all these states. Good. I didn't want to explain this in detail. What I wanted to show that there is a quantity to characterize a qubit, probability of its delocalization, and it is defined by the same function, P of E, probability to have a certain energy loss. Good. Does this answer your question, Sasha? Very good. Let me go and let me, what I wanted to say here. Didn't want to go into all possible details, but just to give an interesting new phenomenon. This system has a transition between, so to say, quantum mechanics and classical physics. One can understand that there is a transition by doing the following. Well, first of all, we got P of E. We understand that it has different powers depending on the impedance of the circuit. We implemented together formula for the rate at certain energy bias between the levels. And we compare this rate with the energy itself in the limit of small epsilon. And if this energy goes if this ratio goes to 0, it means that we have very well-defined states at low energy. So this corresponds to quantum mechanical situation. In the opposite limit, the state becomes too wide, too much spread. So this is some energy level, and it is broadened by gamma. Fine. So here we have a transition, and we know the point of this transition. This happens when this exponent will become two. Yeah. Yes. True. Right. So if the impedance exceeds this critical value, then the qubit won't be a qubit as we used to. It will be a classical system, a classical memory cell, where an electron, if you put it on island, would forever stay over there. While on another side of the transition, we have de-localization. And it becomes increasingly worse a qubit if we approach the transition. But at all impedances below this critical value, we still have de-localization of an electron between two islands. But again, interaction with environment, big impedance of the effective environment, can spoil this picture completely. So, dissipative Schmidt transition has a name tag attached to it. We will recall it yet a couple of times during this lecture. Right. Let me now turn from tunneling of normal electrons to tunneling of Cooper pairs in Josephson junctions. Right, so I look at a kind of a simple system where I have this Josephson junction, and I have electromagnetic environment, which is just simply a resistor. Very similar to what we have already gotten, but here we have tunneling of Cooper pairs superconducting current. Let me recall that Johnson energy can be rewritten in terms of Cooper per tunneling. So here n are different numbers of Cooper pairs transferred through the junction. Anytime we transfer junction, we pay energy, we transfer a Cooper pair in through the junction, we get the energy gain provided by this voltage source, right? That's why the states at different end form a ladder. So if you go through from a higher to lower step of this ladder, you just give energy to voltage source. Very good. This energy is fixed by the voltage applied. All right. But how we can go between the steps of the ladder? This is the tunneling. The tunneling provided by Josephson energy. Fine. All right. Let us now characterize the situation in terms of P of E. This is easy to figure out from what we have already read. Now the tunneling between the ladder steps is accompanied by very certain energy loss, UV. And that means that the rate of this tunneling has to be proportional to P of E, probability of energy loss at this particular voltage. Fine. So from the other hand, the rate is just the current which goes from the junction, current divided by time, because the charge of 2E is transferred anytime the tunneling happens. Fine. Thereby, I can just plot the curve. And if you are attentive, you see that I just reused the picture I have already shown to you. As a picture of P of E, because this current is just proportional to P of E. Good. So what do we see? We see that sometimes the current, if impedance is sufficiently low, current increases at low voltages. And actually, this is what we expect it to do. Why? Because if we forgot about impedance, if we just concentrate on Johnson junction, we would have a supercurrent, final supercurrent at zero energy. So the emergence of this current at voltages just indicates supercurrent. Well, if it goes down, like for this case, something happens with the supercurrent. And indeed, in this case, supercurrent state doesn't exist at zero voltage. A little bit about this function P of E. One has to take into account that now we have tunneling of Cooper pairs rather than electrons. For normal electrons, we have seen that this parameter governs the function P of A. Right, and electronic charge enters here like this. I just write conductance quantum in terms of electronic charge. One has to count, one has to double this electron charge, which means that effective impedance felt by Cooper pairs is kind of 4 times bigger than impedance felt by electrons. Good. So with this picture, let us understand whether we have really supercurrent Josephson effect at 0 voltage. And it all depends. I guess I have some mess up at this transparency. All right. First of all, what we want to understand this transparency, we have current, which is proportional to the rate of tunneling. We divide it by EV to understand whether current diverges at low voltages. Right, and we understand that there is a transition, again, the same Schmidt transition, which happens at this value of conductance. Right, and those are the curves above, at the transition, and below the transition. So for orange curve, we have supercurrent. This supercurrent disappears at the transition point, and then there's no supercurrent at 0 voltage above this point. Right. What does this mean? For orange curve, it in terms of qubit, it corresponds to de-localization of the qubit. And in this case, the phase is well defined. Superconducting phase is a good quantum number. Its counterpart, charge, as we recall from the theory of Johnson junction, is undefined. Remember, there is a relation between superconducting phase and charge, which resembles Heisenberg uncertainty relation between coordinate and momentum. Fine. On another side of the transition, I would assume the opposite. It is a phase which is undefined. And it is a charge which is defined. Right. And it is therefore localized in the space of charge and delocalized in the space of phase. Anyway, the message is that there is dissipative phase transition, and if we put a large impedance in series with Josephson junction, we will kill the supercurrent. Good. Let us since time allows, let us, we still have plenty of time. Let us talk about um, other sort of tunneling. Other start with Washburn potential. I have already told you about. Remember, it describes Josephson junction. And for classical Josephson junction, it means that Josephson junction can be in series of minima in the space of the phase. And we also mentioned the phenomenon of macroscopic how do we call it? I've forgotten the name. Macroscopic tunneling, when the whole Josephson junction as a whole tunnels between this minimum. Indeed, there is a potential barrier, and if there's quantum mechanics going on, there is some amplitude of tunneling through this barrier. Good. What is different from the situation we just considered? That in this case, the junction is current biased. So there is a current source which actually gives the slope of this washboard potential. All right. Let us figure out some model, some simple Hamiltonian, which will describe this situation. We will assume that there is one quantum state in each well of washboard potential. And there will be a variable for us which shows the well, which identifies the well. Look, we also have a ladder similar to what we talk about. Is important distinction. The steps of the ladder are not states of the charge. They're states of different phase. All right. Otherwise, the Hamiltonian very similar. We just have tunneling between the neighboring wells. This amplitude J. All right. Let me also recognize, and that is seen from the shape of washboard potential. Let me draw it here. There is a ladder, and the steps are separated here by something proportional to the current. The current, as we remember, defines the slope of the potential. Therefore, the energy difference between the levels. So I have to look at the formula. It's a pi h bar divided by E current. Current times flux quantum, if I'm not mistaken. Fine. Again, in addition to that, we will have an environment. We will have a resistor, conductor, whatever, which in this case will produce current fluctuations affecting the tunneling. Look, anyway, when we have here phase tunneling, flux tunneling, we have to dispose an energy to the environment. The only point where tunnels is not charge. It is its conjugated variable phase. Sorry for a small interruption. I guess I got something very important. Okay. So how to deal with this? What to do? It is a rather fine trick whereby we can switch between phase and charge, impedance and admittance, so that resistance or conductance, capacitors and inductance. This is a remarkable duality in electric circuits, which is revealed if we compare these two cases. Tunneling of the phase and, as we've seen previously, tunneling of the charge. Let me formulate this. Just by comparing Hamiltonians, which describe these two systems. Well, look at the Hamiltonians rather boring. I could try to make a better story about it, so, but it's just technically simpler to look at the Hamiltonians and to understand that these two Hamiltonians are the same upon the change of notations. But the change of notations is rather drastic. And this change of notations is called charge phase duality. First of all, what kind of change do we have in a variable in which we tunnel? Well, we tunnel between two steps of a ladder in each case. If it's phase, we tunnel by 2 pi. If it's charge, we tunnel by 2e. Well, if it's charge tunneling, we have Josephson energy. If it's tunnel of the phase or some amplitude of tunneling through potential barrier of Fishbone potential, we don't care much of this. It is more interesting to look what happens here when we compare these terms. There is a symmetry between voltage and current. Again, we consider the situation where we apply voltage. We consider the situation we apply current. and we get the same ladder in both cases. That's why we can replace current by voltage and voltage by current, well, with obvious coefficients. All right, how about fluctuations? How about environment? Now we can switch resistance and conductance. We can switch admittance, and this is stays for admittance, and impedance of a circuit. Again, conductance quantum helps to keep it dimensionless, enables the switching. Right, so what is Schmidt transition in this situation? Or just a duality point where this mapping just becomes the same. So what we have on the one part of the transition corresponding to low impedance. Well, we have the phase as we used to have in Johnson Junction. Phase is localized. Dual variable charge is therefore de-localized. Right. And low impedance also applies high admittance, right? It's just high conductance. Good. Let us understand what happens at another side of the transition. Okay. Owing to this duality, we just need to switch everything. So in this case, impedance is high, admittance is low. The phase is delocalized, and the charge is localized. Fine. One also understands from general principles that somewhere the transitions as complete mass, it's difficult to distinguish between charge and phase, whatsoever. But it's important to remember this transition separates two clear limits. One limit is phase well-defined, large Josephson energy. Another limit, charge well-defined, large charged energy. So that's how it goes. Very good. I'm a bit ahead of time, and let me just finish the lecture. Nevertheless, I will have to give a talk at scientific talk in several minutes. That's I better make the lecture a little bit shorter. Let me just tell you that there are many topics related to what we just discussed. In any case, electrons which participate in quantum transport interact with some slow modes, low energy modes, which are present. We look at the electromagnetic environment, and which provide dissipation energy lost to the modes. All right, for electrons moving in the environment, yeah, one can talk about effective impedance. They could actually escape Coulomb blockade. Large liquids, which are electrons in ballistic one-dimensional wires, also case of this general theory. Electrons can be the environmental modes can be fermionic. Electrons could just interact with electron hole pairs, and that gives rise to Fermi singularity and Cone effect. There are interesting things if we depart from tunnel junctions limit and look at the junctions of high transmission zones, as they eventually become tunnel junctions. But okay, there's a variety of topics, and we just touch it a bit when talking about interaction of electrons with the electromagnetic environment. Next time, and that will be the last lecture of this course, we will we will go in the same direction, but instead of dissipation, we rather concentrate on decoherence and relaxation, which is brought by the environment. And that will be very important in this course because we will have to understand the limits of quantum transport. For a larger part of the course, we assume that electrons are waves, that they go from one point they are transported as waves. There are also decoherence processes which prevent this. And in the final lecture, we will look at these processes in more detail. All right, with this, I stop the recording of the lecture. If you have questions, it's time to ask them.